Hello students, so here is a quick video that I had to make on potential energy, chapter 8. Now this is very important for the next exam, so pay attention. First of all, we need to distinguish between two types of forces, the conservative and non-conservative forces. Now conservative forces are those such as gravitational force, where when you take an object from one point to another, you can take it along any path. So you can take it from this point to this point along the straight line path or take it along a curved path. The work done will be the same. So those are conservative forces. Electromagnetic, gravitational, these forces are conservative forces. But on the other hand, forces such as the drag force or friction are non-conservative forces. That means it's exactly the opposite. The work done now depends on the path taken. As we all know, in the case of friction, the shortest path will usually lead to the lowest work done, assuming that all the paths are on the same surface. So as you see in the diagram, when you go from A to B, you can go straight from A to B directly, or you could go along this path that I've shown, which is path 1. If the work done along path 1 and path 2 are the same, then it's a conservative force. So in the gravitational force field, you can take an object straight up, or you can take it along a ramp. The only thing that matters is the vertical height. If it's a conservative force field, like the gravitational field, it only depends on the vertical height. So that's the difference between conservative and non-conservative forces. Now, potential energy is defined as the negative of the work done. Potential energy is the negative of the work done. So delta U represents potential energy and work is W there. And always the change in potential energy is the negative of the work done. So let's take this case where you go straight up. You're going up. The change in potential energy, gravitational potential energy, is positive. That means the gravitational potential energy of the object increases. But the work done by the gravitational force is negative. Whenever the potential energy, gravitational potential energy increases, the work done by the gravitational force is negative. On the other hand, if you consider the object going down, now the change in potential energy is negative. That means potential energy decreases. But the work done by the gravitational force is positive. So that is what you have to understand. How is work defined? Work is defined as the integral of fx dx from initial position xi to final position xf. But since we've already got the relation between change in potential energy and work, we can now say that the change in potential energy is delta U, which is negative of the same thing, because delta U is negative the work. And whenever we consider potential energy, we always take a reference level. Usually the reference is the ground. So at the ground, we take the gravitational potential energy to be 0. So if U is 0 at y sub I is equal to 0, then at any height y, we can show that the potential energy is mgy. Because force is m times a, which is m times g in this case, and the height is y, so it's mgy. That means we're not really interested in the actual gravitational potential energy. We are only interested in the change in potential energy. That's why we take the reference to be anywhere we like. If it is a simple pendulum that's oscillating, we would take the lowest point of the object as the reference, and we will take the potential energy at that point to be zero. Because what matters is that when it goes to one side, the potential energy increases to either side. We are only interested in that change in potential energy. And next we have potential energy of a spring. You know that you can extend a spring, compress a spring, and in both cases the spring kind of objects to what you're trying to do. So the spring exerts a force that's exactly opposite to the force that we apply, and therefore we have to do work. The change in potential energy of a spring is negative integral xi to xf negative kx dx. Why? Because we know that the force in a spring is negative kx, where k is the spring constant, which signals how tight the spring is. For a tighter spring, k is high. So once you put that into the integral, you take the constant out, integrate x dx, you get x squared by 2. And when you substitute the limits, you get the formula as 1/2 k xf squared minus xi squared. Once again, we can take the reference level to be at a point where the initial potential energy is zero, just as in the case of gravitational potential energy. And in this case, you would see that we end up with potential energy as a function of x is 1/2 kx squared. 1/2 kx squared. In order to work out problems, conservation of mechanical energy is a very important tool. And mechanical energy is the sum total of potential energy and kinetic energy. That's what you see there. That is what you mean by mechanical energy, because mechanical energy is of two types, kinetic and potential. And their sum total must always be the same. That's what we mean by conservation of mechanical energy. What does that mean? That means how much ever one decreases, the other must increase. So the change in kinetic energy is always opposite to the change in potential energy. But this is only true for conservative force fields. In other words, the total mechanical energy is a constant, as you can see there. And the change in total mechanical energy is what? Zero, because there is no change in total mechanical energy. So that's a very important tool in order to work out problems. And finally, the most important of concepts is how to get the force from a potential energy curve. Now, potential energy curves are important whether it's in the atomic world or in the macroscopic world. And if you take the slope of the potential energy curve, you will get, in fact, you take the negative of the slope of the potential energy curve, you will get the force. That's what is written here. F of x is negative du of x by dx. So the slope or the derivative of the potential energy curve gives you the force. Now, when it comes to curves, we know that there are turning points in a curve. Let's again go back to the example of a simple pendulum that's oscillating. Now, when the pendulum goes to one side, it stops there momentarily and then returns. Now, that's called a turning point. You know why? Well, of course, because it turns at that point, and also because the kinetic energy is zero at that point. Because what did I say? I said it just stops momentarily. So turning points are those points where the kinetic energy becomes zero. So we have two turning points in the case of a simple pendulum. And then we also have the lowest point at which the potential energy is a minimum. Potential energy is a minimum. And if you draw a graph of this oscillation, you will get a parabolic curve, and at the lowest point, we know that the slope is going to be 0. Because at the lowest point, it's a kind of U-shaped curve, and at the lowest point, it's horizontal, right at that point, and therefore the slope is 0. So, we know two things. Number one, at turning points, kinetic energy is 0. And at the lowest point, potential energy is minimum. We cannot say it's 0, is minimum. And how do we get the force? We get the force as the negative of the slope of the potential energy curve. So we will see as we go forward how we can use this to solve problems. So that is what I've been telling you. At equilibrium points. Now, the lowest point is the equilibrium point because that's where it lies at rest. Or in other words, that's where the forces cancel out. That's the meaning of equilibrium. And the slope is 0. Okay. So now, power. Average power is the rate of doing work. It's simply stated as work over time, or since work is the same as energy. Remember, energy is the ability to do work. So we can also say that average power is the change in energy by the change in time. So it is the energy expended in 1 second. So here is our first problem. In this question, it says, the figure shows a thin rod of length 2.10 meter and negligible mass that can pivot about one end to rotate in a vertical circle. So it's a rod which can rotate about a vertical circle, in a vertical circle. A heavy ball of mass, 8.20 kilograms, is attached to the other end, and the rod is pulled aside to an angle of 22 degrees and released with an initial velocity 0. Now, this is what we would call a compound pendulum. It's not a simple pendulum. It's a rod, and it's oscillating. We have to find the speed of the ball at the lowest point, and then at the B part, does the speed increase, decrease, or remain the same if the mass is increased? Excuse me. Second part especially is very important. The answer is going to be surprising, at least for some. So how do we find the speed of the ball at the lowest point? We know that at the point where we let it go, its kinetic energy is 0. That's a turning point. But at that point, its potential energy is maximum. So as it comes down, its potential energy changes into kinetic energy. So we know that the potential energy at the highest point should be equal to the kinetic energy at the lowest point. Assuming that at the lowest point, we take that as the reference, assume that the potential energy there is 0. So whatever potential energy it had at the highest point becomes kinetic energy at the lowest point. That is the idea. So that's what I'm writing here. At the lowest point, potential energy is 0. That's the reference level. And then there is some trig here. You can see from the trig that, if you look at this right angle triangle, let me try to show you this right angle triangle here. Cosine of theta is L minus H this side, because the total is the length L and this much is the height. So this adjacent side is going to be L minus H divided by L. So you can manipulate that to get this and then make H the subject to get H is equal to L times 1 minus cosine theta. So we got an expression for height in terms of the length and the angle. Now applying the conservation of mechanical energy Ki plus Ui should be equal to Kf plus Uf. But Ki at the turning point is 0 and Ui is Mgy or Mgh. In this case, we know H is what we got here. So substitute that, and K final at the lowest point is 1/2 times mass times velocity squared, which is the formula for kinetic energy. So from there we can solve for velocity, rearrange and solve. We get this formula. It's always going to be square root 2gh, which is what we have. Then plug in the numbers and we would get 1.73 meter per second. That's question number 1. Question number 2. A single conservative force F is equal to 7.0 x minus 12 I newtons, where x is in meters, acts on a particle moving along an x-axis. The potential energy U associated with this force is assigned a value of 28 joules at x is equal to 0. What is the maximum positive potential energy? And at what negative value and positive value is the potential energy equal to 0? So we given the force here. You given the force, we are asked to find the potential energy. Let's do it. We know that the change in potential energy is the negative of the work done. And work is Fx dx. So integral 0 to x Fx dx is what I've written. And when you take the derivative, you're going to get negative 3.5 x squared. Of course, you know how. Because it's 7.0 x squared by 2, right? Negative 3.5 x squared plus 12x, 12 dx. Integral 12 dx is 12x. So that's what we get when you substitute the limits. And then u as a function of x minus u at the reference point, which we have taken to be 0, is this quantity that we got, because if the initial potential energy is 0, then the change is the same as whatever potential energy it is. But we're given that the potential energy is 28 joules at x is equal to 0. So we can use that and find the potential energy at x, which is 28 plus 12x minus 3.5 x squared. Now we know that's a quadratic equation, so if you draw a graph of potential energy as a function of x, this is what we're going to get. And once you get that graph, well, on the y-axis you have force, and x-axis you have displacement or x. Now F is equal to negative du by dx, and we know that at the maximum F is equal to 0. At the maximum, F is 0. Therefore, we set this equal to 0 and calculate x naught. Remember, we are setting the force to be equal to 0. So do not be confused there. We've set the force 7.0 x naught minus 12 is equal to 0. And x naught is therefore 1.71 meter. Once you get that, we can find the potential energy at any point x just by using the value of x naught in the equation that we have above. That gives us 38 joules. Now to answer B and C, since it's a quadratic equation, if you find the roots of the quadratic equation, you're going to get two roots. X is negative 1.6 meter and x is 5.0 meter. So that's where you get the negative and the positive value of x when the potential energy is equal to 0. To get a quadratic equation, we set it equal to 0. That means we set the potential energy equal to zero and solved for it. You know what I'm trying to say? This is the formula for potential energy. And once you set that equal to zero and solve, you get the answer. There is one more problem that I want to do, and this would be the most important problem in this chapter. In the figure, a block of mass 15 kg is released from rest on a frictionless incline of angle 32 degrees. Below the block is a spring that can be compressed 3.4 centimeter by a force of 370 newtons. The block momentarily stops when it compresses the spring by 6.3 centimeter. How far does the block move down the incline from its rest position to the stopping point? And B, what is the speed of the block just as it touches the spring? So the accompanying diagram makes it clear that this block is coming down. It's released from rest and it's on a frictionless incline. So at the beginning, the block has potential energy, and as it moves down, its potential energy changes into kinetic energy. And then at the moment it hits the spring, it transfers its potential energy, which now becomes the potential energy of the spring. Okay? So there is a transfer of energy here. Now, since we've given all those distances, from the diagram, let's label them. Let's label this as L0. That's the initial distance from the spring of the block. It should be from the center of the block. And then this distance, we will call it X0. That's the uncompressed length of the spring. And just to bring it to proper perspective, I'm making that triangle right there. And you can see that the angle there for that triangle is going to be the same. It's going to be theta. That's not going to change. You know what I'm trying to say. This angle here is theta, and this angle is also going to be the same. And so there is this height here. Let's take that height as h and call these points A, B, and C. And from that triangle, we know, because this is theta, sine theta is going to be the opposite side, which is HA, called it height at A, divided by the sum of L0 and X0. So that is sine theta. We are using the conservation of mechanical energy, and we know that the sum total of kinetic and potential is going to be 0. So Ka plus UA, so A is that point at which the total mechanical energy, which is the sum of the potential and the kinetic, should be equal to that at C. So whatever is the total mechanical energy at A should be the same as at C. That's what has been written. At A, it was initially at rest, therefore its kinetic energy is 0. You got that there, plus mgHA is equal to, when it comes down and hits that spring, you know that the potential energy of a spring is given by the formula 1/2 kx squared. In this case, because the spring is compressed by x0, we're going to call it 1/2 kx0 squared. And what happened to kc? The block stopped because it said the block momentarily stops when it compresses the spring by 6.3 centimeter. So that's why we do not have anything for k sub c, which is 0. And then we have this formula from which we can now make HA the subject. We make HA the subject, we get that. And then we can substitute the values of K. Where did I get K as 10,900? You see, it says the spring can be compressed 3.4 centimeter by a force of 370 Newton. Now, what is spring constant? Spring constant is the force required to compress it by 1 meter. So using 370 and 3.4, after changing 3.4 into meter, it will become what? 0.034. you divide 370 by 0.034, you will get the value of K. So that's why I have 10,900. Now, X naught in meter is 0.063 divided by 2 times the mass of the block is 15 kilogram, G is 9.8, and that calculation gives 0.147 meter. So the height of position A is 0.147 meter. Since we've got the height now, we can use the formula that we had before. L naught plus X naught is HA by sine theta. That's just rearranging that equation. We can now find L naught plus X naught. So I get L naught plus X naught because I have HA and divided by sine 32, and that gives 0.28. So how far does the block move? It moves a total distance of L naught plus X naught, which we have now. So let's move on to the B part. What is the speed of the block just as it touches the spring? So L naught is 0.277, which was, before rounding off. I rounded it off to 0.28. So from that we got L naught, that's the distance that it moved down. And then using delta y, or the absolute value of delta y, is L naught sine theta. We get this as the answer. So, because we know, now delta y is just, in this case, it's going to be whatever came down by, that's L naught, so we've got to have a little triangle there. And then that's the height that it dropped through when it finished moving through L naught. Okay? Now we have to find the speed of the block just as it touches the spring. That's where we use the conservation of mechanical energy. You know that the total change in mechanical energy is 0. There is no change in mechanical energy, so the total change in mechanical energy is 0. And initial kinetic energy is 0 at the height at the position A. So we have 0 plus mgHA, which is the potential energy at that location. And then when it comes and hits at B, we're trying to find the speed at B, right? So that's why I have put it as 1/2 mvb squared plus mgHb. Remember, even at the position B, it still has some potential energy. Now rearrange all that and you also find that the mass is going to cancel out, right? And you get this for the velocity. Remember I told you it's always going to be square root 2gh in this type of a problem. And you get the answer as 1.49 meter per second. So I think inside or approximately in 30 minutes, I've given you the crux of this chapter, the most important part of this chapter. Now you got to do the homework, use the textbook, and on exam 3, we're going to have chapters 8, 9, 10. Hopefully you'll all do good, much better on exam 3. Thank you.